In this video, I'm going to go through some U substitution practice problems just so we can get a better handle on them. I'm going to start by going over the homework from February 23rd and then do some other practice problems. So this was example number 1, find the integral of x times sine of x squared dx. So remember that this integral symbol and this dx is just telling you to take the antiderivative of whatever's in between there. And the problem is I don't really know how to deal with this, right? So right now, U substitution for us is like a backup plan, where I can make a substitution to make probably this part easier to look at so that I can take the antiderivative. So the first thing I want to do is make a substitution, and I look for, generally the composition of functions. So I take a look at this sine of x squared. I don't know what to do with him, but if I could just make it look like sine of u, some other variable, I know how to take the antiderivative of that, right? That just goes to negative cosine. So I'm going to start by letting u be equal to x squared. My next step is always to differentiate u. So the derivative of u with respect to x, du over dx, is, remember I could bring the exponent down and multiply and subtract 1 from it. Generally, this form isn't too useful to us though. So if you remember from class, I multiply both sides by dx to just get du is equal to 2x dx. Now you got to think to yourself, our integral right now looks like this. It looks like the integral of x times sine of u dx. And my goal is to try to get everything in terms of u, so I want to eliminate all of my other x terms. Remember, multiplication is commutative, so it doesn't really matter what order I write this in. So it might be more useful to me to write it like this, just to make it more obvious what I still need to get rid of. I need to find an expression that represents x times dx, so I can replace it with something with a u, so that I can integrate. Now, if I'm looking what I have here for du, I'm pretty close, right? 2 times x dx. So to fix that, I'm just going to divide both sides by 2 here, to get that 1/2 du is equal to x times dx. So instead of writing x dx at the end there, I'm just going to write it as 1/2 du, because that equation down there says that those quantities are equal. So right now I have the integral of sine of u times 1/2 du. If you remember your rules for constants, I could bring that constant on the outside of the integral. And the whole point of U substitution is to get this to look like something I know how to work with, whether it's going to be a reverse power rule or one of those special antiderivatives. And here, this is just a special antiderivative. I know the antiderivative of sine is just negative cosine plus c. Now, the only thought I need to have is that they didn't give this to me in terms of u, they gave it to me in terms of x. So I'm going to make that substitution and plug back in for u. So my final answer here is negative 1/2 cosine of x squared plus c. Now, you'll never have to guess if you did this correctly, because you could always take the derivative to see if you did this correctly. So just as a check, I won't do this for all of them, but if I take the derivative of negative 1/2 cosine of x squared, remember this is a chain rule. The derivative of cosine of something is negative sine of that something. Derivative of the outside times the derivative of the inside function. The derivative of x squared is just 2x. And remember, the derivative of any constant is 0, so that's just going to go away. So I've got a negative times a negative, so that's going to be a positive 1/2 times 2x times sine of x squared. And you should notice what's happening here. Well, 1/2 times 2 is just 1, so all I'm left with is x times sine of x squared, which is exactly the function we started with. So I could always check my integral answers just by differentiating to make sure I applied the rule correctly. For number 2, we had a function that looked a little bit different, but the process is still the same. Cosine of ln of x over x dx. And if you're asking who should I make u, I'm always looking for the composition of functions here, right? I don't know what to do with cosine of ln of x, but I would know what to do with cosine of u. So I'm going to make the substitution that u is equal to ln of x, and again I'm going to differentiate both sides. The derivative of u is equal to Remember, ln of x, the derivative of that is just 1 over x. And I'm just going to move the dx to the right-hand side, so I'm going to skip the step where I multiply both sides by dx. So here's my integral right here. I've got cosine of u over x dx. And I still need to get rid of this x in the denominator and that dx. So one way you could rewrite this to make it more obvious what I'm trying to get rid of is that this is the integral of, if I separate that fraction, of cosine of u times 1 over x dx, right? Because that would keep that x in the denominator. And with u substitution, usually this is pretty satisfying because that will always work out where you either have exactly what you need with du or something pretty close to it. So 1 over x dx is the same thing as du. So I'm going to replace that just with du. And the du, all that means is just to integrate whatever's in between the integral symbol and du. So again, cosine of u is one of those special antiderivatives where the antiderivative of cosine is just positive sine. Again, because if I differentiate sine, I'll get cosine. And they didn't give it to me in terms of u, so I'm just going to replace u with whatever u was. So that's ln of x plus c. So that's my final answer for the second homework problem. For the third one, it's a little bit trickier about who to make u. But the concept is still the same. I'm looking for where is my composition of functions. So it looks like in the denominator, that sine of x squared, I don't know how to deal with that. But if that was just like 1 over u squared, I could make that u to the negative second, and I would know how to work with that. So those are my thoughts when I look at something like this, when I'm trying to think of who I should make u. So let's see what happens there. If I let u be equal to sine of x, and I take the derivative, remember the derivative of sine is just cosine, my integral currently looks like this. The integral of cosine of x over, instead of sine of x, I'll just write that as u squared dx. And again, if you're having trouble seeing what's here, separate it. I've got a cosine of x, I've got a 1 over u squared, and I've got a dx. But for us right now, it might make it easier to write the cosine next to the dx, because if you look at du, that's precisely what we have there. So du is equal to cosine x dx. And cosine x dx are the two x terms that I still need to get rid of. So instead of writing cosine x dx, I'm just going to replace it with du. This will always happen where du is exactly what you want, or you would need to divide out a constant like we did for number 1, where it was pretty close, we just needed to divide out that 2. So here, if I make that substitution, I have the integral of 1 over u squared du. I'm going to rewrite that just so I know how to work with that. I'm going to write it as a negative exponent instead, just so I can apply the reverse power rule. So that turns into, if I add 1 to the exponent, negative 2 plus 1 is negative 1, and divide by the new exponent, plus c. And remember, I just made u sine of x. So this is negative sine of x to the negative first plus c. But I think I could simplify a little bit further. Is that technically correct? Yes. But remember, a negative exponent just means to put it in the denominator. And negative 1 over sine x is actually just one of the reciprocal trig functions, right? 1 over sine is the same thing as cosecant of x. So if I wanted to write a final simplified answer, it could look something like that.